I will start in a few minutes. I will just wait for a few more minutes to see if anyone joins and then I'll start. So I'll start now. And if anyone joins later, they can just listen to the recording later on. Right. So this is the second live session for the course on NMR spectroscopy for structural biology. Actually, this session was supposed to be taken this Monday of this week, but due to some circumstances, it had to be postponed. So that is why I guess people could not join. But like the first session, this will be recorded and uploaded. So you can just go through it in your own time and come back with your doubts in the next session, which will be in the coming Monday. Okay. So this week, I'll again, like last week. So last week was week one. In this week, I'll discuss the 5 videos of week two. I'll go through them, summarize them, and at the end, again, similar to last week, I'll solve a few practice questions. So this is what we have already learned in the previous live session, but I'll quickly go through it because it's kind of like a continuation. So what we had seen is the nucleus is surrounded by an electron cloud. What this electron cloud does is that it kind of shields the nucleus from experiencing the full effect of the external magnetic field B0. So B0 is the external magnetic field applied by the spectrophotometer, and it is in the upwards direction. But the field actually experienced by the nucleus is less than B0. It is given by Bi, or B effective, and it is B0 into 1 minus sigma I, where sigma I is said to be the screening constant of the environment. Why this happens is because the electrons are negatively charged particles, and they are moving. So moving charged particles generate a field, and this field will be in the opposite direction to the external field. So the net field experienced by the nucleus is actually, so if I consider this B dash, the field induced in the electrons, nucleus is actually experiencing a net field of B0 minus B dash. And this can be written as, in terms of the screening constant, this formula here. Now, so the nucleus experiences a field less than the actual field that is applied. Now, depending on the electronic environment around the nucleus, the field applied can decrease a lot, or so if the field, 1 second, I think someone wants to join. Yeah, so I'll continue what I was saying. So just a recap of the previous class. So the field experienced by the nucleus is actually less than the field that is actually present, that is supplied by the spectrophotometer. And the shift is represented by a variable called chemical shift, or delta I. So in the NMR plot that you have, in the x-axis, you have this chemical shift plotted. And the formula of this, so you take a reference compound, something like TMS, which we discussed in the previous class, and we take the frequency at which TMS is excited as nu R, and nu I is the frequency of the sample peak that we are looking at. And dividing that by the spectrophotometer frequency nu 0, you get the value of delta I, or chemical shift. If the delta I is greater, that means it is said to be more downfield shifted or deshielded. And if the delta I is less, it is said to be upfield shifted or more shielded. So this is an example that Sir has already discussed in his lecture 6. I'll just cover it. So here is a vinyl chloride where there's a C double bond C. And so there are 3 kinds of hydrogens here. One which is on the same carbon as that of the chlorine, and of the 2 other hydrogens, this one is cis to the chlorine, and this one is trans to the chlorine. So they have been written as A, B, and C because they are in 3 different chemical environments. Now, we have seen in the previous class that chlorine is an electron withdrawing group having a minus I effect. So the hydrogen which is closest to the chlorine will be most de-shielded. So it will appear most to the left of the spectra. Indeed, in the spectra seen here, you can see the B hydrogen appears most to the left. Then between A and C, how do we distinguish? If we consider distance through the bonds, then it is equal. Both A and C are 3 bonds away from the chlorine. You can consider 3 bonds like this or like this. So in terms of bonds, they are not different. But if you consider the electronic cloud around chlorine, so you can consider that there's an electron cloud forming around chlorine, and this electron cloud is kind of shielding the proton Hc because they are both on the same side. So Hc is getting shielded compared to Ha, which is at a larger distance away from the electron cloud of chlorine. So just 1 second, I think someone else wants to. Yeah, so as I was saying, the proton that is cis to the chlorine is getting shielded by the electron cloud around the chlorine. And so Hc will appear more upfield shifted compared to Ha. So between Ha and Hc, A is more downfield shifted and C is the most upfield shifted. So this is how, depending on the chemical environment around the proton, they appear at different places in the NMR spectrum. Then, so the reference compounds, these are common reference compounds used in different NMR spectra. So last class we were discussing about TMS, that is tetramethylsilane. The reason it is such a good reference compound is that all the 12, so there are 4 methyl groups and 3 hydrogens on each. So there are 12 hydrogens and all 12 hydrogens are equivalent. So this compound will give only one peak in the NMR. And it will be a very high intensity peak. So you can easily distinguish the peak of TMS from any other peaks of the samples will appear at lower intensities and much farther away. So you will not confuse the reference and the sample peaks. And the other advantage of using TMS is that these 4 methyl groups, they will donate electrons. These 4 methyl groups, the carbons are very much shielded. So that is why we can assume TMS to be 0 because it will appear most along the left of the spectrum. So it is a good reference because it can be considered as a chemical shift of 0. But the problem with TMS is that it's very non-polar. So if you have some polar compounds, so basically what we do is that we mix the reference along with the sample. But if the compound is soluble in a polar solvent like water, TMS will not be soluble in water. So in that case, in those cases, a more polar reference is needed, and that is this TSP, that is trimethyl silyl propionate. So this molecule that you can see here, there are 3 methyl groups. So trimethyl silyl from the silicon and propionate because there is a propanoic CH2CO minus propionate group. Now only the CH3s are maintained as hydrogens and rest are deuterated because again we want only one signal for the reference. So these 3 methyl groups are equivalent and so they will appear as a single peak in the spectra. And so this can also be as a good reference. Similarly, there are other options like DSS. In DSS, again, you deuterate the other protons so that you have only one peak for the reference. And there are several other options where, so reference compound is basically somewhere compared to that, you take the chemical shifts of your other samples. So now the reference can be used in 2 ways. One is the internal standard method where you have your NMR sample tube And inside the sample tube, you have both your sample and the reference. And you put the sample tube inside the spectrophotometer and you get the spectra. In the same spectra, you have the peak of the reference and the peak of the sample. Generally, the reference is very upfield shifted, so it comes around 0 to 1 ppm. So there is no confusion between the reference and sample peaks. This is called an internal standard method because the reference and the sample are both inside the sample tube. The other method is called an external standard method. In this case, you have two different sample tubes. In one you have the sample that you want to analyze, and in other you have the reference material solution. Both these are put in the spectrophotometer and two different spectra are obtained. Then these two spectra, you can compare and assign the chemical shifts of the sample based on the chemical shift of the reference. Here it is called an external reference because the reference is in a completely different sample tube. That is, it is outside the sample that you're analyzing. So this is comparatively a more complicated process because you have to get two separate spectra and then overlap them in the computer or compare them. But in what cases it is used, mainly suppose your sample is very sensitive. That is, in the presence of the reference, if you have the reference and sample inside the same tube, the sample is either reacting with the reference or it is decomposing. In that case, this external standard method is used to preserve the sample. So we saw about the 1H chemical shifts in the previous class. So different functional groups appear at different chemical shifts. And these are characteristic of these functional groups. So if you remember this basic area where each functional group comes, then you can analyze an NMR spectra and predict that what are the functional groups that are present in the unknown sample. Like you can remember the COOH proton is very downfield shifted around 11 to 12 ppm. And why it is that downfield shifted, you can imagine COOH. So not only is there a strong electron withdrawing effect, but there can also be hydrogen bonding to another COOH molecule. So just imagine another COOH molecule. So because of hydrogen bonding, this hydrogen is even more deshielded and it appears at very high ppm values around 11 to 12. Similarly, your aldehyde proton, which is basically the proton attached to a carbonyl group. So there can be resonance in the carbonyl group and this will withdraw electrons away from the hydrogen. So the aldehyde is also quite downfield shifted around 9.5 to 10. Then you have your aromatic and vinylic protons. That is the aromatic ring and vinylic is the double bond. So we saw the ring current effects in the previous class. Basically what happens is that when you have an applied magnetic field, suppose in the upward direction, it will cause the electrons in the benzene ring to rotate and this will give rise to a ring current. Because of this ring current, an induced magnetic field will be formed, and we know according to Lenz's law that any induced magnetic field will be in the opposite direction to the applied magnetic field. So you can see the induced magnetic field is in the downwards direction and the applied magnetic field is in the upwards direction. But in order to complete the magnetic lines, you can see that so magnetic lines are closed. So even though they are in the downward direction in the middle of the ring, in order to close the line where the hydrogen is, the field is upwards and the applied magnetic field is also upwards. So the hydrogen is actually experiencing a net field. If we consider the applied magnetic field as B0 plus the induced magnetic field as Bi. So the hydrogen is experiencing a field of B0 plus Bi. So the hydrogen is getting more deshielded. which is why the aromatic or vinylic protons are very much deshielded compared to the saturated system. And then you have the protons attached to polar atoms like halides or oxygen or nitrogen, which are slightly more downfield shifted. And the most upfield shifted protons are the saturated hydrocarbons because there is no electron withdrawing effects in them. Now, when you imagine this kind of ring system, instead of the XYZ coordinates that are traditional, there is another coordinate system called cylindrical coordinates that we can consider. Basically, you imagine a cylinder. So the face of the cylinder is basically the face of the benzene ring. And you can imagine a cylinder extending in the Z axis. So the Z direction is given as Z. And in the XY plane, you have another axis called rho. So rho and Z are called the cylindrical coordinates. Now, this plot that you have here, basically it's a plot of rho versus Z. And what they have done is that wherever the chemical shift is constant, lines have been drawn. So suppose, let us just consider we are going along Z. So if we go along Z, we have seen here, so imagine a point here which is along the Z axis. This point will experience a net field of B0 minus Bi, because in this point, the induced magnetic field is downwards and applied magnetic field is upwards. So this will actually experiencing a shielding effect. That is, the chemical shift value will be positive. So you can see these values written here, 1.00, 2.00. These are basically chemical shift values. So chemical shift values along the Z direction are positive because in the Z direction, a shielding effect is observed. That is, the molecule is getting more upfield shifted. Now, along rho, we have already seen, so hydrogen is present in the rho direction. So this is your rho direction and where your hydrogen is present. So along rho, there is a deshielding effect. So your chemical shift values will be negative. That is why you can see along rho, these values that are written on the lines, they are all negative. That is -2, -1.50, like that. This is because there is a deshielding effect along rho. This kind of lines are called isoshielding lines because along the line, the chemical shift value is same. So suppose you follow this line that I'm showing the cursor on right now. Any point on this line will have the chemical shift value of plus 0.2. Any point on this line will have the chemical shift value of 4. So these are called isoshielding lines. Iso meaning same and shielding meaning the chemical shifts because they have same chemical shift values. So similarly, you can have ranges for the 13C chemical shifts. The only difference is that carbon has a much wider range of chemical shifts. So in hydrogen, it was mostly between 0 to 12. But in carbon, it goes up like greater than up to 250 around it goes. So the range is much wider, but more or less the order is same. By that I mean the here also you saw the carbonyl compound was one of the most downfield shifted, and same is the case here. You have the carbonyl compounds like aldehydes, ketones, carboxylic acid, ester, and amide, which are the more downfield shifted. After that, you had your aromatic and vinylic groups, and they come around here. So again, you have your aromatic and vinylic groups. So the basic order is the same because similar effects are affecting the chemical shift here as well. like the ring. So imagine you have a carbon atom here. You are this carbon atom on the ring, which is basically an aromatic carbon. So this carbon atom will also face the same deshielding effect that this hydrogen atom was facing. So the aromatic carbon will also be deshielded. Sorry. And that is why you can see the aromatic carbons are deshielded compared to saturated alkanes. So similar effects are prevalent in the 13C NMR as they are in the 1H NMR. Now we'll come to a new concept, that is spin-spin coupling. So basically, when you have, so hydrogen itself has a spin, and if you have two hydrogens near each other, the spins of one hydrogen can interact with the spins of another hydrogen. Two kinds of interaction are possible here. One is the dipolar interaction, but this is something we will discuss later. What we will discuss now is the interaction that happens through the electrons in the intervening bonds. So in this example, between and HA and HB, there are three bonds. One second. Between HA and HB, there are three bonds. And so this is said to be a 3J coupling because HA and HB are separated by three bonds. Now, what happens here? So, if you consider only one hydrogen, according to hydrogen has an I value of half. And so, in presence of a magnetic field, there are two energy levels, M plus half and M minus half, which we have termed as alpha and beta. We have discussed this extensively in the previous class. Now, when you have a second hydrogen atom near it, there can be, so you can have different kinds of combinations. You can have both up, one up, one down, one up, and both down. There are four different combinations possible. And how this is denoted, so we know that whenever it is paired like this, the energy is lower. So this will have lower energy. So whenever opposite spins are paired up, the energy is lower. So this line is alpha. When alpha pairs with beta, it goes to a lower energy. And when alpha pairs with alpha, it goes to a higher energy. Similarly, beta can pair with alpha and it will go to a lower energy. And beta can pair with beta and that will go to a higher energy. So you have, for the four different orientations, you have four different energy levels. Now, which transitions are allowed? Again, this is something we saw in the previous class, that the rule for the allowed transition is that delta M must be plus minus 1. And this is called single quantum transitions. In this case, how do we calculate the M? Is that, so when there was only one proton, M was plus half and minus half. But in a two proton system, the total M is considered. So the lowest energy is alpha beta. For alpha, it's M half, beta is M minus half. So you add half and minus half and you get total M as 0. Next energy state is alpha alpha. So you add half plus half and you get net M as 1. Similarly, for beta alpha, net M is again 0, and beta beta, net M is minus 1. So in these are the values of M that we will consider when we use this rule delta M is plus minus 1. If you do that, you will see that there are only two allowed transitions. From alpha beta, you look at the blue lines. From alpha beta, you can go to beta beta, because alpha beta has M0 and beta beta has M minus 1. So this is a allowed transition. Delta M is minus 1. Again, from alpha alpha, you can go to beta alpha because M is changing from 1 to 0. So these are, so upward transition and downward transition, they are considered between the same energy level is considered as the same transition. So there are only two allowed transitions. So what will happen is that instead, earlier there was only one allowed transition. So we were getting a spectra like this. Now there are two allowed transitions. So this spectra will split up like this, which is what we are observing. Earlier, we were getting a ppm like this at delta B. Now that will split up into two, uh, uh, which are the allowed transitions shown here. Similarly, the other proton, so proton B is getting split by proton A into two parts, one with higher and one with lower chemical shifts. Similarly, proton A will also get split by proton B into two separate lines. So instead of two single peaks, we are getting two peaks for each proton, and this is called a doublet. Now, this we saw was 3J coupling. And the frequency difference between this pair, that is written here as JAB, is the spin-spin coupling constant. So this was 3-bond coupling or 3J coupling, and it has a value of 3 to 15 Hertz. Coupling can also occur with only one bond separation, like if you have 1H and 13C directly attached, or 1H and 15N directly attached. That is only one bond separation, and it is called a 1J coupling. And they have different frequency values, which you can remember. A 2J coupling is when, suppose you have carbon with two hydrogens. These are called geminal hydrogens, and they are separated by two bonds. This kind of coupling is called a 2-bond coupling or 2J coupling. And the weakest coupling is the 4-bond coupling or 4J coupling. It's also called meta coupling because it occurs between hydrogens which are at meta positions on the aromatic ring. So here they are separated by 4 bonds. And so you can see as the number of bonds are increasing, 1J, 2J, 3J, 4J, the values of the coupling constant are decreasing. This is because more the number of bonds separating the atoms, the coupling will be weaker, and so the value of coupling constant is also decreasing. Beyond 4 bonds, there is it is too far away to interact, and so 4J is the maximum. 4-bond is the maximum number of separation that can exist between two hydrogens that are coupling. So this we saw was coupling only between two spins, HA and HB. What if you have a 3-spin system? So you can have 3-spin systems, and they can be arranged in two ways. One can be a linear system like AMX, and another can be a triangular system, A attached to M attached to X, like a cyclopropyl ring or something. So in the linear system, proton A will be split by proton M, and it is splitting into a doublet because when there is one proton interaction, it will split into a doublet. And the splitting constant we'll call as JAM because it is A interacting with M. Similarly, M will split into 2 because of A, and again the splitting constant will be JAM. Now each line of M will further split into 2 because M is in the middle and it is interacting with X also. So each line of M further splits into 2 lines, and the new splitting constant is JMX because it is due to the interaction of M with X. So earlier when you had 2 lines, we called it a doublet. Now that you have 4 lines, we call it a doublet of doublet. And X is again only interacting with M. So X will only split into 2 parts, forming a doublet. And the coupling constant will be JMX because it is getting split by m. So if it is a linear system, the splitting will be as a you will get two doublets, and the middle proton will be doublet of doublet. Now if it is a triangular system, in the triangular system, each proton is interacting with two other protons. M is interacting with A and X is interacting with A and M, and so on. In the linear system, we saw that if one proton is interacting with two other non-equivalent protons, it forms a doublet of doublet. So in this case, each of the protons will form a doublet of doublet, and so you will have three doublet of doublets. Now suppose, so doublet of doublet we are writing like this. But suppose these middle two lines are merging, then it will appear as a triplet. So these two lines, if they are merging with each other, you will have one line in the middle which has higher intensity and two smaller lines. So in that case, it's called a triplet. So here again, if you look at the allowed transitions, so in case of three, when there are when it is splitting into three energy levels, so when all three are alpha, so in case of two energy levels, alpha was the lower and beta was the higher. In case of three protons, when all three are alpha, it is the lowest energy. And when all three are beta, it is the highest energy. And similarly, when two are alpha and one is beta, there are three possibilities. Beta can be on either side or it can be in the middle, and they are all degenerate energy levels. And the other is that when two are beta and one is alpha, and here also there are three degenerate energy levels. In this, so this rule is constant, which is the delta m is plus minus 1 rule is constant. So using that, again, you can find out that which are the allowed transitions. So here there are 12 allowed transitions. So you can see the green lines, they are allowed transitions. The blue lines are also allowed transitions. And finally, the black lines are also allowed transitions. So in this case, there are 12 allowed transitions. So now we have seen chemical shift and we have seen spin-spin coupling. The other property is called as the intensity or integral. So suppose you have ethanol molecule, which is CH3CH2OH. In this case, if we look at the chemical shift, the hydrogen which is connected to O, it is directly connected to the electronegative element O, and so it will be the most downfield shifted, which we can see here. Then the CH2 is closer to O, so CH2 will come after that, and CH3 is farthest away from O, so it is the most upfield shifted. Then in terms of splitting, if we see, the general rule for splitting is that if you have n neighboring protons, you will have n plus 1 peaks. So CH3 has two neighboring protons and 2 plus 1 is 3. So CH3 will appear as a triplet. Now, how many neighboring protons does CH2 have? You might think it has 4. That is 3 from CH3 and 1 from OH. But the thing is, OH proton is actually exchangeable. So it can exchange proton with the D2O solvent, and so the OH proton does not participate in splitting. So CH2 only has 3 neighboring protons and 3 plus 1 is 4. So CH2 appears as a quartet, that is 4 peaks. And OH, again, because the H on the alcohol is exchangeable, it will not take part in spin-spin coupling, and so it will appear as a singlet. So that is the spin-spin coupling part. The third part is the intensity ratio, which represents the number of hydrogens that make up the peak. So basically the area under the peak, integral is taken of that area. And for OH is to CH2 is to CH3, the integral gives a ratio of 1 is to 2 is to 3. because there is one OH proton, there are two CH2 protons, and there are three CH3 protons. So the third property of the NMR spectra is this integral or intensity. Now we look at some other properties of the NMR spectra. So we know that in the presence of an external magnetic field, if the I is half, then you will have two energy levels, plus half and minus half. Now, these two energy levels, again, which we have called as alpha and beta, the population in these energy levels will be different. Suppose we consider the population difference, that is alpha minus beta, population difference as n. So n can be defined as n0, 1 minus 2 exponential minus t by t1, where t1 is your spin lattice relaxation and n0 is your population difference at equilibrium. So this equation we have already seen in the previous class. So basically, how do we arrive at the exact, so we know this transition from alpha to beta will occur at a certain frequency. How do we arrive at that frequency? We can do two things. We can sweep the field. This means that suppose we have a spectrometer providing a certain B0, we can change the value of B0 provided, keeping the frequency constant, or we can change the value of frequency, keeping the B0 constant. So what will happen that as we are changing the value of frequency, the moment the frequency matches with the energy difference between the two levels, the transition will occur from alpha to beta, and we will be able to see the NMR spectra peak. But the problem is with this is that in any, so these kind of machines are called continuous wave NMR spectrometer or CW NMR. So the time that it takes to sweep 1 hertz of frequency is 1 second. So suppose we want to sweep 1,000 hertz of frequency, it will take 1,000 seconds, which is close to 16 minutes. So this is an extremely time consuming process, because just to check which frequency will be the resonance frequency where the promotion from alpha to beta will occur, it is taking 16 minutes. So this is a very time consuming process, and that is why it was thought that something better is needed, like this kind of continuous wave NMR spectrometers are needs to be improved so that the time can be reduced. Now, another thing which slows down the process is that when we are changing the magnetic field, the delta E changes, because delta E is gamma H B0. So changing B0 will change delta E. And if the energy difference between alpha and beta changes, then the population difference will also change. So in order to come back to the equilibrium population, it will take some time, which is the spin lattice relaxation time. And this is also an extremely slow process. So the time is a lot of time is needed, not because the spectrometer itself takes a lot of time to sweep through the entire frequency range, but also because at each value of B0 that we are setting, the delta E is different. And if the delta E is different, the population difference between alpha and beta are different. And so every time we are changing B0, alpha and beta will try to go back to their original or equilibrium population difference. And the time that it takes to go back to the equilibrium population distance is called spin lattice relaxation time, and it's a very slow process. So here we have another term that is important, is called the signal to noise ratio. So basically, in an ideal NMR spectra is where the baseline is completely flat and then you have your peak and again the base. But this is very ideal. We don't observe like this. Normally we observe a baseline where there is a lot of aberrations. So this is called noise. And then you have the sample peak, and again you have a lot of noise. So the signal to noise ratio is defined by, first of all, you see this line that is drawn in the middle of the noise. It's called mean noise level. So in order to define the signal to noise ratio, in the numerator, you take the peak height above this mean noise level. So once you take an average of the noise, and that is your mean noise level, and from that line you go to the top of the peak. That is your numerator. And in the denominator, you take the maximum peak in the spectra minus the peak separation in noise. Doing this and multiplying by 2.5, you will get the signal to noise ratio. Now, suppose you have, when do you have, like, how do you improve signal to noise ratio? Is by increasing the number of times you are scanning the NMR. So, like we saw before, there are two energy levels, alpha and beta. Now, if the population difference is low, then this delta E is low, and we will get a very low so if the population difference is low, it is only the population difference that is giving us the peak. So suppose alpha has a population of n plus 9 and beta has a population of n. So it is these 9 protons that is giving us the spectrometer peak. So if this number is very small, then we will get a very small peak. So in order to increase the intensity of this peak, we have to take the scan of the sample several times. And each time we will get a signal, we will add these signals up to get a stronger signal. That is why the more number of times we scan the sample, which is also called number of sweeps, the better the signal to noise ratio improves. The exact correlation is that signal to noise is directly proportional to square root of the number of sweeps. Now, suppose we want to enhance signal by noise by 10 times, then we have to increase number of sweeps by 100 times. And that will take a lot of time. We just saw that for scanning. So if one sweep is taking, we saw that one sweep through the 1000 hertz is taking you 16 minutes. If you have to do this 16-minute process 100 times, then it will take 1600 minutes, which is an absurd time. You cannot spend 1600 minutes just trying to measure the NMR of one molecule. So that is the problem with the continuous wave NMR instrument. Other things is that suppose you are doing an experiment for 1600 minutes, then you have to maintain the stability of the sample. Many samples can get decomposed in such a long time. Then the spectrometer will have to maintain the maintain a equilibrium field throughout. That is also difficult. Then you will need very high concentrations of the sample. And finally, you have nuclei like 13C and 15N, which have very little natural abundance. So you can see 1H has a large natural abundance of 99.9%. So that is not a problem. But in 13C, the abundance is only 1.1%, and 15N, the abundance is 0.37%. So already you are getting a very small peak because the difference between alpha and beta is low. Now, if the abundance of 13C is also so low, this peak will be even much more smaller. So as the natural abundance of the nuclei decreases, it will be very difficult to observe those nuclei using this kind of process where you are scanning the same NMR multiple times in order to improve the signal to noise ratio. So this kind of process can mainly only be used for things like 31P, which has 100% abundance, or 19F or 1H. But for nuclei with a low abundance like 13C and 15N, you will not observe any signal at all. because even after adding several signals, the intensity is not enough that you can observe it. That is when the improved type of NMR was found, which is the Fourier transform or FT-NMR. In this, what happens? So here you have a picture of a radio frequency. So this is, suppose this is an electromagnetic wave which is supplying a radio frequency energy to the system. Now you apply this radio frequency only for a short time tau, which is a few microsecond. That is represented by this kind of a rectangular shape, which is called, and it's called a pulse. So what the pulse basically means that for a short time tau of a few microsecond, you are switching on the source which is providing you a radio frequency energy, and after the time tau is over, you're switching it off again. So what happens when you do this is that you are able to excite all the nuclei at the same time. And so you can see here that if you do Fourier transformation of this, so basically what Fourier transformation, this is a graph of intensity versus time. What Fourier transformation does, it is a mathematical function which transforms the time axis into frequency axis. So this kind of intensity by time pulse, if we do a Fourier transformation on that, it will give us a intensity by frequency pulse. So you can see that all these frequencies are being supplied to the system. So we are exciting several nuclei at the same time. And suppose we normally we restrict the system into a small frequency, so that suppose we choose only this area which I've shown by this arrow. So within this small arrow, the amplitudes are more or less equal. So all the nuclei will be excited with the same amount of energy. Now suppose we are keeping this tau time, that is the pulse, we are keeping it on for 10 microseconds. So 10 microseconds, if you do 1 by tau, it is 10 to the power 5 second inverse, and which is otherwise 100 kilohertz. So second inverse is basically hertz. So 1 by tau is 100 kilohertz. So if you keep the radio frequency on for a time of 10 microsecond, in 10 microsecond, it is able to scan a range of 100 kilohertz. Earlier, what did we see? That in order to scan 1000 hertz, 1000 hertz is just 1 kilohertz. So in order to scan 1 kilohertz, it was taking 16 minutes. And now by using this kind of Fourier transform, we can scan 100 kilohertz in 10 microseconds. So the range has increased significantly and the time has also decreased significantly. So from 16 minutes, it has only become 10 microsecond. So the entire range of 100 kilohertz of frequencies are excited at the same time. So you are exciting all the nuclei at the same time. That is another advantage of the Fourier transform method. Now, in the Fourier transform method, so basically, we saw in the previous class that we have a laboratory frame of reference and we have a rotating frame of reference. Now, any nuclei, it is precessing about its axis. The Larmor precession that we learned about has a frequency of omega naught. So this kind of cone is formed and the frequency basically moves around the cone in a precessing motion called the Larmor precession, and this has a frequency omega naught. Now, if we apply a radio frequency pulse, the radio frequency is represented by this circular motion here. and that has a frequency of omega. So the radio frequency is represented. So the radio frequency that we are supplying by this pulse is represented by this h1 e to the power minus I omega t, where h1 is the amplitude. So amplitude is this length, e to the power minus I omega t. Omega is the frequency. So this is how the radio frequency is represented with respect to the Larmor precession of the nucleus. Now suppose your observer is standing on this radio frequency line. So the observer is not stationary, but he is moving along with the radio frequency. So with respect to the observer, he will notice that he will notice a frequency of omega naught minus omega. So suppose the observer is standing on this radio line and looking up. So he will observe, he is also moving in this direction, and the Larmor precession is also happening in the same direction. So from relative motion, the observer will observe a frequency of omega naught minus omega. This is said to be the precessional frequency in the rotating frame, that is written as omega r. And omega r can be written as minus gamma hi, where gamma is the gyro-magnetic ratio. Now, if we represent this by this kind of a diagram. So initially we had the magnetization completely in the z direction, which we are writing as H0. But when the pulse is applied, the radio frequency is applied, then you have a H effective. So the H effective is basically the effective magnetic field experienced after the pulse is applied. And different nuclei will have different H effective depending on the value of its Larmor frequency. So normally what will happen is that when you have this kind of a rotating frame of reference, now suppose your Larmor frequency and your frequency of the radio frequency wave is matching. So this omega in the z direction will become 0. So your magnetization along the z direction will completely vanish, and your resultant magnetization will only lie in the xy direction. And so this is a better representation of that. Initially, the magnetization was completely along the z direction. Then what we apply, what is called a 90-degree pulse. It's called a 90-degree pulse. And what this will do, it will force the net magnetization M to come down to either the x or y axis, depending on whether the 90-degree pulse is applied along the x or y axis. But once it comes to the x and y axis, so the process is coming is not simply like it's up and suddenly it jumps to the xy axis. It comes in this kind of a spinning motion where gradually the z component reduces. So z component is reducing and x component or y component is increasing. This kind of a spinning motion happens where as it is spinning, the z component is decreasing and the x or y component is increasing, till finally your entire magnetization lies along your x or y axis. So the angle traveled by the magnetization is called the flip angle or theta. We can have the most common kind of pulse is the 90-degree pulse, where from the z axis it is flipped to the x or y axis. Now, suppose we remove the pulse. We saw earlier that after time tau, the pulse is removed. So in that case, again from the X or Y axis, it will try to go back to the Z axis. This process is also not a matter of simply jumping back. So you can see this diagram here. It was initially in the Y axis. Then slowly, after the pulse is switched off, the Y component is reducing and the Z component is increasing. So Y component reduces, Z component increases. You can see that is what is happening here. The Y component is slowly reducing and Z component is increasing till you again regain your original magnetization completely along the Z direction. Now, the detector is kept along Y direction. So what will the detector see? The detector is measuring the magnetization along Y. So initially magnetization will be, we start the detector as soon as the magnetization comes to the Y axis. So initially the magnetization observed. So what we do, we have this pulse, and once the pulse is completed, then we measure the signal. So that kind of signal is called a free induction decay, or FID, and it is maximum at the beginning because your entire magnetization has come down to the y-axis. So the initial magnetization observed is maximum. Now as time goes, so in x direction it is time, as time goes the signal intensity decreases because the magnetization is going back to Z. That is, the Y component of magnetization that the detector is measuring is reducing, and so gradually it will completely decay to zero. This is called the spin-spin or transverse relaxation. So when we carry out, so different FIDs are obtained for different protons. So you can see, suppose this curve, suppose we get for one proton. For another proton, we are getting this curve. And so FID is basically a superimposition of the different curves obtained from the different protons. In the x-axis of FID, you have time. So you can see the signal is decaying with time because the magnetization is going back to the z-axis. If you do a Fourier transform where in the x-axis instead of time you have frequency, then you will get what you see in the conventional NMR spectra. You get different lines at different frequencies. So a Fourier transform will change the FID to what we observe as the NMR spectra. Now, so we can see the difference between the Fourier transform NMR and the continuous wave NMR. So continuous wave NMR, we have already seen it takes a long time. One scan is taking 500 seconds to do. And Fourier transform is a much faster process because in 1 second, we can scan the entire sample 500 times. So it is a much faster process. Now, if the number of scans are increased, signal to noise will also improve. And so you can see in continuous wave, you cannot distinguish what is signal, what is noise. Everything is coming, signal to noise ratio is very poor. But in this upper spectra, which is the Fourier transform spectra, clearly you can see the signal peak and these are the noise peaks. So signal to noise ratio is also greatly improved because you're able to scan the sample 500 times in just 1 second. So if signal to noise is improved, you can collect the signals of nuclei with very low abundance like 13C or 15N. It was difficult to do these nuclei using the continuous wave process because the abundance was very low, but you can do them using the Fourier transform process. And low concentration is enough because you're able to scan the sample multiple times in a very short time. Similarly, because it is a very short length process, you can study kinetics of, suppose you have a reaction and you have to measure the NMR at very small time intervals. Because the Fourier transform process is so fast, you can do that using the Fourier transform process. Secondly, finally, if you have unstable short-lived molecules, if you try to measure that NMR using the continuous wave process, the molecule itself might degrade before you get the NMR. But because the Fourier transform process is so fast, it can measure the NMR even for unstable short-lived molecules. So these are all the advantages of the Fourier transform NMR over the continuous wave NMR. Now, another thing is, how do we increase the strength of the magnetic field? So, what is used in the NMR spectrometers are superconducting magnets. Basically, in superconducting magnets, resistance is very low. I mean, ideally it should be zero, but actually it is a very low value. So what happens is, when the current is induced in the electromagnet, the current does not decay, and so the magnetic field is very long lasting. So suppose you have a normal magnet. In that magnet, if you suppose you have an electromagnet, and in that magnet you are passing a current and a magnetic field is forming. If it is a normal magnet, the current will die out due to resistance and the magnetic field will also become zero. But in superconducting magnets, the current does not die down because resistance is zero, and so the magnetic field is also very long lasting. So these kind of superconducting magnets are used in NMR because they are very stable and they can create very high magnetic fields with very high homogeneity. So homogeneity is an important factor we have already seen, because if the field is inhomogeneous, then the NMR spectra will have a lot of aberrations. So because of the good homogeneity of the superconducting magnets, it is used. So normally, in order to maintain the superconducting condition, the temperature needs to be very low, typically less than 6 Kelvin. That is the temperature where the resistance goes to zero. That is, it becomes superconducting. In order to maintain that low temperature, a bath of liquid helium is used. So you can see liquid helium is given here. So this coil is your wire through which you are passing the electric current, which is becoming the electromagnet. Now, this wire is submerged in liquid helium, so that liquid helium has a temperature of 4 Kelvin, which brings the temperature of this wire down and makes it superconducting. But liquid helium is very expensive. So in order to prevent the liquid helium from evaporating, there is a kind of layer of liquid nitrogen around the liquid helium. Now, liquid nitrogen has a temperature of 77 Kelvin, so it is not low enough to make the magnet superconducting. But what happens is, because of the low temperature maintained by the liquid nitrogen, a kind of heat shield is formed. That is, the liquid nitrogen is keeping the liquid helium cold and preventing the liquid helium from boiling away. After that, there is a layer of vacuum. This is again to further reduce the heat flow. Because liquid helium is so expensive, all kinds of measures are taken to prevent the liquid helium from evaporating. So both the layer of liquid nitrogen and the vacuum layer are basically there to cool down the liquid helium and prevent it from evaporating. You have a board in the middle passing through the electromagnet coil, and this board is where the sample is inserted. And it is important to note that this board is at room temperature. So if we are measuring the NMR of the sample at room temperature, it is only the coil which is around the board which is kept at a low temperature so as to make it superconducting. So when this kind of condition is maintained, the superconducting magnet can produce very strong and stable magnetic fields, which will give us a very uniform NMR. So this is again the basic layout of the NMR instrument. You have your sample. So the pulse programmer is basically telling the radio frequency source that what value of radio frequency or what energy of radio frequency should be supplied to the sample. The radio frequency transmitter or RF transmitter is supplying the radio frequency to the sample and exciting it. And the sample is already there in the magnetic field. So the magnetic field is interacting with the sample magnetic field, and it is giving rise to the NMR, FID. The FID is received by the receiver, and then it undergoes a lot of data processing in order to get the NMR spectra that we know. So basically, this kind of FID is obtained first, and then within the data processing and computer system, the Fourier transform functions are carried out so that we can get the NMR spectra that we recognize. Other than that, there are systems to control the magnetic field. So suppose we want a NMR with better resolution, then we take a higher spectrometer frequency. So we can control the magnetic field. Then there is something called a shim system, which adjusts for variation in the magnetic field. So suppose that despite using a superconducting magnet, there is some inhomogeneity in the magnetic field. And we saw in the last class that inhomogeneity in the magnetic field can cause line broadening. So in order to prevent that, the shim system maintains a homogeneous magnetic field so that you can have sharp lines in the spectrum. So this is again the very basic outline of the FT-NMR spectrometer. Now there are certain properties of the NMR spectra, which I will discuss in the following slides. Just give me 2 minutes. The first concept is that of offset or carrier frequency. Basically, suppose the frequency of your sample is coming somewhere here and your spectrometer frequency is quite far away from that. You can see there is a large distance shown by this blue arrow between the spectrometer frequency and the frequency of the protons in your compound. Then this distance is called the offset. So what we do is that through the computer, the spectrometer frequency is adjusted so that it falls within the frequency of your protons, because only then it will be able to excite the protons of the compound. So it is adjusted digitally so that the spectrum so the in the spectrometer, you have an electromagnet. If you vary the current flowing through the electromagnet, you will be easily able to vary the magnetic field. So the spectrometer frequency or magnetic field is adjusted so that it falls within the frequency of the protons. This adjustment is called an offset, and where the new frequency of the spectrometer appears is called the carrier frequency. The second thing is the RF pulse. So in RF pulse, we have to adjust this tau is the time for which the pulse is supplied. And this also has to be adjusted so as to get the best spectra. We will see later how the time affects the spectra. The next thing is the free induction decay. So we know that initially the magnetization was along the Z direction. When the RF frequency is supplied, it comes in the transverse plane in the y-axis. And your detector, you can see the antenna receiver here is along the y-axis. So initially the signal picked up along the y-axis detector is the highest. And as the time is passing, the magnetization returns back to the z-axis. So the signal detected by this receiver decreases till finally it becomes zero when the magnetization has completely gone back to the initial magnetization along the z-axis. So this kind of curve where you have intensity with time is called your free induction decay. And depending on whether the detector is placed along y or x axis, the wave that is obtained can be described by a cos wave or a sine wave. So cos wave is basically where at 0 it is maximum because cos 0 is 1, and sine wave is where at 0 it is 0 because sine 0 is 0. So depending on whether the detector is placed along x or y, and whether the 90-degree pulse we are supplying is forcing the magnetization along x or along y, we will either get a sine wave or a cosine wave. And this kind of wave is called the free induction decay. So each of these free induction decays, basically the Fourier transform is carried on so that instead of time, you have frequency in the x-axis. So basic, you don't need to know the mathematics of this. The basic thing you need to know is that if it is a cosine wave that is maximum at the beginning, then Fourier transform will give rise to an absorptive signal, that is a signal only in the positive direction. If it is a sine wave where initially the value is 0, Fourier transformation will give rise to a dispersive signal where you have both positive and negative components. Similarly, if you have a cosine wave but starting from the negative direction, then you have an absorptive signal but in the negative direction. And similarly, if you have a sine wave but in the negative direction, then your dispersion will also be in the opposite direction. So out of all these signals, this is the one that we most use. In NMR spectra, this is the one that you will see. So what the computer does is that it will filter out all the other kinds of signals so that you can focus only on this kind of absorptive signal. Another point is the single channel versus quadrature detection. So we have already seen that what is the carrier frequency. So we have seen that the spectrometer frequency, we adjust it somewhere within the range of the frequency of the protons, and that is what we are calling the carrier frequency. Now, if we adjust the spectrometer frequency such that it is at one end of the spectral width, so all your proton peaks are coming within this range. This is called the spectral width or SW. And your spectrometer frequency, that is the carrier frequency, is adjusted to the right of this range. Then it is called one detector or single channel detector because it only has to detect in one direction. But suppose your spectral width is again this, and your carrier frequency is somewhere in the middle, then it is called quadrature detection because you have to detect both in the left and in the right. That is both positive and negative frequencies. So in order to do that, two detectors are needed, and that is why we called it a quadrature detection. So this is another setting, that whether a single channel detector is needed or a quadrature detector is needed. And basically that depends on whether you are, if you are adjusting the spectrometer frequency so that it is at one end of the spectral width, then single channel detector is fine because you're only picking up signals in one direction. But if your carrier frequency is in the middle of the spectral range, then you need two detectors because you're picking up signals both in the left and in the right. Another thing is signal digitization and sampling. So you have an FID like this, but how are the data points actually collected? So basically, the spectrometer picks up several data points, uh, keeping the time between each data point as constant. And this is called the dwell time, or DW. And then after it collects all the data points, it fits a curve to the data points, which is what forms our FID. So once again, the time between two consecutive data points in the FID is called the dwell time, or DW. There is a theorem called the Nyquist theorem, which says that at least 2 points per wave are needed to be collected to represent the frequency. So the question can be that there are data, what is the minimum number of data points you need to collect so that you can, you can see here, this is a superimposition of two frequencies. Suppose nu1 and nu2. Because there are two kinds of waves, you will do Fourier transform of this and it should give you a spectra like this, suppose. So what is the minimum number of points you need to collect for each frequency in order to properly get the FID so that you can do a Fourier transform? Nyquist theorem says that at least 2 points are required per wave. So normally what we do is that we take the dwell time for the largest frequency. So these two waves that you see here, we normally take the time in such a way that at least 2 points are collected for each frequency, and then it is enough to reconstruct the FID and we can do the Fourier transform to get the spectrometer frequency. Now, what will happen if there is a frequency outside our chosen spectral width? So, the spectral width is the frequency range that we are sampling. Suppose we are sampling a frequency range shown by the arrow here, but there is a frequency which is falling outside that range. So how will we know that? The way to know that is that in this case, it is a single channel detector because your spectrometer frequency is at one side and you are detecting frequencies only in this side. So in this case, what will happen is that the frequency that is lying outside your spectral width will appear as a negative frequency. So the moment you see this negative frequency, you will realize that the spectral width taken is not enough and you have to take a new spectral width which is larger. So this kind of signal is called a folded signal, where you will get a distorted phase. So phase of all your signals are supposed to be positive because we are only choosing the positive. We are only choosing this component, which is positive absorptive. So phase of all your signals are supposed to be positive, but if suddenly you get a negative phase, what that indicates is that it is a folded signal. That means your spectral width is not large enough and you need to take a larger spectral width. Similarly, in case of quadrature detection, where you are having the carrier frequency somewhere in the middle, and it's quadrature detection because you are scanning in both directions. In this case, if you have a frequency lying outside, so this is your spectral width. If you have a frequency lying outside your spectral width, again the phase will change and you will know that you need to increase the spectral width in order to properly pick up all the frequencies. So like this, so the NMR instrument operators, they do this by trial and error. the safest way to do this is choose a large enough spectral width in the beginning and then optimize it later. So you can choose a large spectral width such that all the signals are included. And then slowly you reduce the spectral width. And the moment you see that this kind of negative signal or folded signal is appearing, that means the spectral width needs to be larger. This kind of folded signal will only appear when the spectral width you have chosen is too small. So this is actually the way to set the spectral width to a proper value so that all the signals are scanned and they appear in the proper phase. Next is your signal averaging and pulse repetition rate. So basically, as I said, we scan the sample multiple times, right? To get a proper signal to noise ratio, we scan the sample multiple times. So we are applying a 90-degree pulse, we are getting an FID. Then again, we are applying a 90-degree pulse and we are getting an FID. Like this, multiple FIDs are collected and summed up in order to get a strong enough signal to noise ratio. The time between two consecutive pulses is what we are considering as TP. Now, what happens is that suppose we have put 90-degree pulse. So we know that when we put 90-degree pulse, the magnetization comes down from the Z into the Y direction. And then slowly the magnetization goes back. Now, suppose we have not given TP long enough. That means before the magnetization is going back, we are again exciting it. If we do it like that, then there will be a lot of problems because you are not allowing the system to go back to the equilibrium state, and before that you are exciting it again. So see, basically we are collecting multiple scans, so we want the initial point of each scan to be the same. Because what we will do, we will take, suppose there are 3 FIDs, we will sum up these FIDs and we take the average. So we need the initial point of each FID to be same. So it is very important that the magnetization goes back to the equilibrium condition and only then we apply the second RF pulse. Again, we let the FID completely decay to 0 and only then we add the third RF pulse. Otherwise, what will happen is that one FID and another FID will merge and then it will be very difficult to separate it. So as you can see, the starting point of the second pulse may not be the same as the first pulse, but it is very important to maintain the starting point as same, because only if the starting point is same, then we can properly add and average them. So we need to optimize the time between two pulses and the angle, this flip angle. So flip angle is basically generally we take 90 degrees, which is where from Z it is coming to Y. So we need to properly optimize both the time between the pulses and the flip angle so that we allow the system to come down to equilibrium before we apply the second pulse. So normally what happens in this is that there is the X component of magnetization, or that is the perpendicular component, can be defined by this equation, which is mx is m0 sine beta 1 minus E1 in the numerator and 1 minus E1 cos beta in the denominator, where E1 is exponential minus Tp by T1, where Tp is the time between two pulses and T1 is the spin lattice relaxation time. So if you plot this, you have Tp by T1 in the x-axis and beta optimum in the y-axis. So here what you will see is that this kind of curve comes. That means we need to choose the beta optimum in such a, so cos of beta optimum must be equal to E1, and E1 is e to the power minus Tp by T1. So we don't need to go into the derivation of this. So basically, if you just differentiate it and equal to make it equal to 0, you can find the beta optimum. So we don't need to go into the derivation of this. Basically, this is the formula that comes. And only when we maintain the beta optimum will we get maximum signal to noise. So suppose you have a system where your T1 is large. That is, your spin lattice relaxation is very large. Where this happens is somewhere like quaternary carbons. So if you have a carbonyl, so you have a carbonyl system. This is a quaternary carbon because it is not at, this is a quaternary carbon because it is not attached to any hydrogen. In this kind of carbon, T1 is very large. If T1 is large, then Tp by T1 will be small. And if Tp by T1 is small, then you can see, so suppose if Tp by T1 is small, you will come to this graph and you will see the beta optimum is less than 90. So basically what this means is just we cannot blindly apply a 90-degree pulse for every experiment, because it may so happen that we are applying a 90-degree pulse, but the FIDs of one scan is merging with the FID of the second scan. In order to prevent this, what we must do is that we should know the T1, and according to the T1, we should set, according to the T1, we should set the time between the pulses to be long enough that the pulses FID does not merge. And if the Tp by T1 is small, we should just follow this curve. So suppose Tp by T1 is coming somewhere around 2. Then we draw a normal to the curve, and then we draw the normal to the y-axis. And whatever the value of beta optimum we get, that is the pulse we should be setting. So that formula of beta optimum determines that what should be the flip angle. So we have discussed the case of 90-degree where from Z it is going to Y, but that is an ideal case. In other cases, you should always calculate the value of beta optimum before you set it. Then there are certain things like data processing. So suppose in an FID, we are not collecting the full FID. So suppose we saw that in an FID, we are collecting several points, and the time between, so we are collecting several points, and the time between the collection of consecutive points is the dwell time, or DW. So suppose in this FID, we have collected n points, and the time between each point is DW. So n into DW is the total time that it takes us to gather this FID. Now, suppose the FID is actually decaying here, but we are collecting only up to here. So we are collecting a truncated FID. What this will do is that it will cause some distortions at the baseline. So the moment we see distortions at the baseline, like you can see here, this means that we have not collected the full FID. We have collected a truncated version of the FID, which is now causing the distortions. So how to overcome this is that how to clean the baseline. Suppose one way is obviously to increase the time for which we are collecting the FID. But suppose that is not available to us, Then what we do is that, so this is the full FID shown in red. We are only collecting up to here. So we are only collecting the FID up to here. So what we can do is that you saw in the spectrometer, you have this data processing part. In the data processing part, there are several mathematical functions which can be used, performed on the data to obtain the cleanest signal. So in that data processing part, you multiply the FID by a function which will go to 0 at the last data point. So instead of the FID suddenly truncating, if you multiply it by a function that is going to 0, then the FID will be forced to go to 0 at the point of truncation, and that will remove all these distortions. So I'll just repeat once. If you have an FID and you are collecting, you are not waiting for the FID to fully decay, you are only collecting a truncated version of the FID. That will cause distortions at the baseline. Now, how to remove the distortion at the baseline is a process called digital filtering. This is done by the data processing unit, and what it does is that it will multiply the FID by a function which is going to 0 at the point of truncation of the FID. So this point in where I'm holding the cursor right now, that is the last data point that we have collected. Now, if we multiply a function that is going to 0 at this data point, then the FID will also be forced to go to 0, and that will remove all the distortions at the baseline. So this does not have to be done manually. There are several functions available in the data processing unit of the computer to do it, and this is called digital filtering. Then there is something called zero filling. So basically, suppose after the FID is finished, so we are truncating the FID here, but we want a cleaner signal. Then what, suppose we have collected n points in the FID, what we can do is that we can add n zeros after the point at which FID is becoming 0. So this does not require, so up to this we have collected the data, we have collected n points, but suppose our signal to noise is still not good enough. So what we can do, we can add n number of zeros after this last point. Then the total number of points will become 2n, and this improves the resolution of the spectra. So you are not spending additional time to improve the resolution of the spectra. You are simply adding zeros at the end, and that improves the resolution of the spectra. And this is called zero filling. So these are basically just different tricks and techniques which can be used to obtain the best possible spectrum. Then, of course, there is phase correction. So the ideal situation is where you have either only absorptive or only dispersive. But sometimes you get signals which are a mixture of absorptive and dispersive. So absorptive will be simply like this. Dispersive will be equally up and then equally down. But what if you have a signal which is mostly up but little bit down? So this signal is mostly absorptive, but there is a mixture of dispersive inside it. This is called a phase error, and it needs to be corrected. So there are different ways of correcting the phase error. Basically, suppose we have there are different ways of correcting the phase error. The ideal case is where you have the magnetization in the Z direction, and then the complete magnetization comes in the Y direction. But sometimes it may happen that you have a component of magnetization that is not exactly in the y direction, rather it is somewhere in the xy plane, then the angle that it forms with the y-axis is called the phase. And the moment you have something like this, you can break it up into x component and y component. And that is where your phase error comes. Another way of phase error is, suppose, so you're collecting points in the FID. But instead of collecting from T0, because of some disadvantage in the machine, you have started collecting points a little later. So originally, so there are two ways in which phase error can come. One, which we just saw, is that the ideal case is where the magnetization in Z is completely moved to the Y direction. But in real case, instead of lying completely in the y direction, that is, it should be zero phase at time t0. Instead of that, the magnetization comes somewhere along the xy plane, and there is a phase error of theta. So we take the angle with y as theta, and this is the phase error that is formed. Another way in which phase error can come is that, suppose the data, instead of taking from time t0, because of some problem in the machine, we have started collecting a little bit. So suppose this small time shown by the arrow is t. So instead of time t0, we are collecting at t plus t0. So in ideal case is where from z it has completely come to y, that is at t0 your entire magnetization is along y. But in the real case, what happens is that uh, instead of T0, we are collecting from T plus T0. And what this will cause is that the different spins. So in the real case, you have, suppose you have 3 protons shown by 1, 2, and 3 here. In the ideal case, proton 1, proton 2, proton 3 are all in the y-axis at t0. But when you have a time delay, t plus t0, then proton 1, 2, and 3 will separate out. So 1 is here, 2 is here, 3 is here. They are separating out. So this is called a frequency dependent phase shift, because depending on the frequency of the protons, they are separating out. And they are having different phases. So you can see the angle with the y-axis that we are calling as theta or phase is different. So this is another way in which phase error can happen. The final concept that we'll talk about today, which was discussed in week 2, is basically what happens when you have a sample in a solvent. So suppose you have a sample in water. Now water has a huge number of protons, and so the water signal will be very large compared to the sample signal, and you will not be able to see both together. So basically what happens is that data in the instruments which store your data, there is an analog to digital converter, and these can only store data up to a certain limit. The most commonly used one is called a 12-bit digitizer, and the 12-bit digitizer can store a number which has the largest value of 2047. So your ratio of the big signal to the small signal must be less than 2047. Otherwise, your data will not be able to store both signals. But in case, so I'll show you what happens is that, so only when the ratio of the large signal to the small signal is less than the limit allowed by the digitizer will both the large and small signals be able to be saved. What happens actually is that suppose you have a sample in water. You can see this example shown here. You have the sample in water and the ratio of proton in water divided by the ratio of proton in the sample is huge. It is 10 to the power 5. So this ratio is so large that the sample signal gets suppressed completely. It appears as noise and you can only see the water signal. This kind of problem is called a dynamic range problem, where your small signal is getting lost. You can only see the signal of the water or solvent. So the way to overcome this is called solvent suppression. Basically what you do, the NMR experiment is where you apply a 90-degree pulse, you get an FID and you record the FID. One thing you have to do before that is you apply a soft RF on the solvent signal. So what this radio frequency will do, the radio frequency shown in blue, it will excite only the solvent protons and it will completely saturate the signal of the solvent protons. So if the solvent protons are saturated, so if you remember what saturation was, you have the energy level alpha and beta. Saturation is when alpha and beta are equally populated. So if you have 2 electrons on beta, you will have 2 electrons in alpha. And at that time, the NMR signal becomes 0. Because, so what you do, you apply radio frequency equal to the frequency of the solvent. And you cause this kind of saturation condition in the solvent. So if you do that, the solvent signal will become 0. And the 90-degree pulse and the FID will only detect the sample signature, which is what you want. So this kind of thing is called a pre-saturation, where you are saturating the sample signal and making it 0 so that the signal of the sample is enhanced. The other method for solvent suppression is called inversion recovery. So in this case, again, you have your 90-degree pulse and your FID. But before this, you apply a 180-degree pulse and you give a time tau. So what happens? Your initial magnetization is along the Z direction. When you apply a 180-degree pulse, the magnetization of your water as well as the magnetization of your sample undergoes a rotation of 180 degree to come in the minus Z direction. Suppose your water is this red line and sample is the green line. After this, you allow a time tau, which is called T1 or longitudinal recovery. So you adjust tau in such a way that the water component becomes 0, but the sample component is slightly there in the positive or negative region. If you adjust tau in such a way that your water component is 0, then when you apply the 90-degree pulse and collect the FID, you will collect the signal of only the sample and the signal of water will be completely reduced. So this technique you can use when your water and the solvent have different T1 values. So if water and sample have different longitudinal relaxation values, then your water can go to 0, but your sample will be there in either the positive or negative direction. And the moment your water goes to 0, if you apply the 90-degree pulse and collect the FID, you will be able to collect the FID of only the sample and completely suppress the signal of water. So this is another method called inversion recovery. Inversion because you are rotating the magnetization by 180 degree, and recovery because you are allowing the magnetization to go back. This technique can only be used when the longitudinal relaxation time of water and sample is significantly different. Because if the longitudinal relaxation time of water and sample are similar, then both will become 0 at the same time, and then you will lose the signal of both water and the sample. So that is a condition for this inversion recovery, that the T1 values have to be very distinct. So that is basically covers the summary of week 2. We will continue with more ways of solvent suppression in the next lecture. But before that, I'll quickly go through some sample problems. So these are basically the problems in the week 1 assignment. So I'll go through them. The first question is asking, the decay in NMR signal is due to what? So we have already seen that this decay is due to spin-spin relaxation, because when we apply your RF frequency, the magnetization is forced. Magnetization is initially along Z and it is forced to come to Y. And then as the magnetization is going back to the equilibrium position, that is, the Y component is reducing and the Z component is increasing. So initially Y component is maximum, FID shows maximum values, and as your Y component is reducing, FID intensity is also reducing. This is called spin-spin relaxation time. So FID is basically your NMR signal, and according to the spin-spin relaxation time, FID is gradually becoming zero, because spin-spin relaxation time is the time that it takes for the magnetization to go back to the Z-axis. And once magnetization is in the Z-axis, FID will be zero because your detector in the Y will not detect anything. So the spin-spin relaxation time is what is allowing the spin to go back to the Z-axis and causing a decay in the NMR signal. So the answer is that decay in NMR signal is due to spin-spin relaxation, that is A. Then you have more the shielding effect. What happens to the chemical shift? Basically, more the shielding effect, lower the chemical shift. So we have seen that you can have a more shielding effect means the nucleus is surrounded by a large number of electrons. The nucleus is highly shielded. If the nucleus is highly shielded, that means your applied magnetic field B0 is greatly reduced. The nucleus is highly shielded, so it is feeling a magnetic field of B0 minus Bi, which is the induced magnetic field. Highly shielded means that the induced magnetic field is high, so the nucleus is experiencing a very weak magnetic field. And we know that if the magnetic field is weak, we know that splitting between alpha and beta, this difference is gamma HB0. B, that is B effective. So if the magnetic field is low, the splitting is low. And if the splitting is low, your delta value or splitting is low means your frequency is low, and frequency is low means your chemical shift is low. That means it is moving in the upfield direction. So shielded by electrons means that your delta value is low. That is, it is moving in the upfield direction. So more the shielding effect, the delta value is low. So lower the chemical shift. So the correct answer is A. Then you have that in an NMR experiment, the radio frequency is oriented in which direction? So the correct answer here is B. We have seen that in an NMR experiment, the initial magnetization is always along Z. We apply a radio frequency pulse shown here, and that forces the magnetization to come down to the X or Y axis. And this is a 90-degree pulse. So 90-degree is basically the angle which the magnetization is going through. The magnetization is going through a 90-degree angle to come to the X or Y axis. And once it comes to the X or Y axis, it is detected by the detector. And then slowly it will again go back. Slowly it will again go back to the Z axis, and your detector signal will decay. So the pulse that needs to be applied is a 90-degree pulse. That is what the question is asking. The radio frequency is oriented. The answer is 90-degree to the main field, that is B. Then it is asking about the frequency range of chemical shift of proton in a 500 megahertz spectrometer. So here the formula you have to use is the chemical shift formula. So chemical shift is frequency of the sample minus frequency of the reference by spectrometer frequency into 10 to the power 6. Spectrometer frequency is 500 megahertz. Now we can write this difference of frequency as delta nu equal to, it will become chemical shift into 500 megahertz divided by 10 to the power 6. We can assume chemical shift range to be around 10 ppm because that is what delta value is always in ppm, and because it is saying proton we know goes up to 12 to 15 ppm, we are just assuming a value of 10 for easier calculation. So if we put the value of 10 over here, we will find the frequency range to be around 5 kilohertz. So if we are taken so basically the frequency range is coming in terms of kilohertz, which is your option C. So your correct answer is option C. Then you have a question asking that T1 relaxation is what? So T2 relaxation we know is spin-spin relaxation. T1 relaxation is actually spin lattice relaxation. So what spin lattice relaxation was is that when you are supplying energy to a system, the population difference between upper and lower levels are changing. But eventually the population will go back to the equilibrium population that is there. And that is called your spin lattice relaxation. So suppose your proton is getting promoted from the lower level to the upper level. That is this black line. So the energy for this promotion, it will take from the lattice. And eventually the proton will again relax back to the ground state shown by the red line, and it will emit an energy, and this energy is taken up by the lattice. So this is called relaxation because it's coming back, and it's called spin lattice relaxation because the energy is supplied by the lattice and it is also taken back by the lattice. So another name of the spin lattice relaxation is the T1, or it is also called longitudinal relaxation because it is along the z-axis. So the T1 relaxation is referring to the spin lattice relaxation, that is B. Then you have a question asking that a nucleus with spin 3/2, what is the number of allowed transitions? So spin 3/2 means I is 3/2. We know the value of M will range from minus I to plus I. So minus 3/2, minus half, half, and 3/2. The selection rule is that delta M is plus minus 1. Then the allowed transitions possible are 3/2 to half, where there is a delta M of 1. Half to minus half, again there's a delta M of minus 1. And minus half to minus 3/2, where there's a delta M of minus 1. So the red lines shown are the only possible allowed transitions. So there are 3 allowed transitions. So the correct answer is B, that is 3. Then you have a question asking, what does the radio frequency do in an NMR experiment? So the correct answer is that the radio frequency promotes both upward and downward transition of spins with equal probability. So in the previous class, we had defined a term P, which we called as radio frequency induced transition probability. And we had derived some kinetics, and we had seen that the probability when a radio frequency is there, the probability of alpha going to beta is the same as beta coming to alpha, and probability of both are P. So that is what the question is asking. what does the radio frequency do? It can promote both upward and downward transition with equal probability. That is the answer, that is B. Then you have the question that radio frequency induced transition probability is proportional to what? So here the formula to remember is that the radio frequency induced transition probability P is equal to 1/4 gamma squared H1 squared, where gamma is the gyromagnetic ratio and H1 is the amplitude of the radio frequency. So if you have a radio frequency, this is your H1 amplitude. So this is the formula to remember. So clearly radio frequency induced transition probability is proportional to H1 squared, which is the square of amplitude of radio frequency. That is your answer C. Then you have the question that what factors contribute to line width. This is something we have discussed in a lot of detail in the previous class. Basically, the factors contributing to line width is, first of all, the lifetime in the excited state. And the lifetime in the state can be affected by spin lattice relaxation or spin-spin relaxation. So we know that spin lattice relaxation enables the molecule to relax in a longitudinal direction from alpha to beta or beta to alpha. And spin-spin relaxation enables the FID to decay. Both of these relaxations basically bring the molecule back to the equilibrium situation. So it is affecting the lifetime of the molecule in the excited state. And so both these relaxation times affect the line width. Secondly, the line width is also affected by field inhomogeneity. If the magnetic field is not uniform, then different regions will experience different frequencies, and so the line will be broader. So A, B, and C, all three options contribute to line width. So the correct answer is option D, which is all of the above. And I think this is the last slide. Yeah. So it is asking the width of the line at half maxima in NMR spectra at low RF power is proportional to what? So basically the formula to remember here is that T2, that is the transverse relaxation time, is 1 by pi W half. W half is called the full width half maxima. So you have the maxima here. You take half of the, this is the maximum height. You take half of the maximum height and you take the width of the spectra. You can see this width of the spectra at half of the maximum height. That is represented by W half. So if you take 1 by pi W half, you will get T2. That is the spin-spin relaxation or transverse relaxation. So in other half, the width of the line at half maxima, so they are talking about W half, is proportional to what? It is proportional to T2. That is the spin-spin relaxation. So the correct answer is option B. So that covers all the lectures of week 2, and it covers 10 sample questions from week 1. So I'll upload the recording as well as the slides by tomorrow maximum. And this coming Monday, 12th, we'll cover week 3. So I think that's it, and I'll end the class now.